안녕하세요. 굿모닝. 네, 안녕하세요. 굿모닝. 음.
Recording in progress.
Oh, sorry. Yeah, I didn't notice. Thank you for letting me know. I didn't know that the mic was muted. All right. So what I just said is just the introductory stuff. Like so far, we've talked about autoencoders, variation autoencoders, GAN, which were all based on fully connected network, basically. So CNN, which is today's topic, is the first non-fully connected network that we're going to talk about. After this, we're going to talk about RNN and also transformers and whatnot. And today's topic is CNN and some variants, 1D, 3D. And there are some very well-known training techniques for CNN, but it is a general technique, but they were specifically designed or tested on CNN architectures, which are BatchNorm, batch normalization, and Dropout. And if we have some time after that, we can talk about some well-known architectures. Especially, I think ResNet is very worth paying attention to. So hope we can have some extra time left. Right. So CNN. Um, this is something that I've only read from the papers, but how like CNN was the architecture of CNN was or design of CNN was biologically motivated. So it's like how human visual perception works. Basically, there's like eye which receives the photon and it generates like electric signal, and then it gets from like the V1, V2, V4 IT, like which are V1 is all about like edges and lines, so very low level features, and then it slowly builds up those features to get the final like image or semantic, which is like human face or a dog or like cat, like something more on the high level abstract like space. So based on that, we would like to also have an architecture that gradually builds this kind of like like visual perception. And I think the very first, really first CNN that came out in the world was of course, Jan LeCun's LeNet 5. So Jan LeCun, you can see all the like famous names like Benjio and Leon Buteau and Jan LeCun. And it's a very simple 5-layer network compared to like ResNet 50 or ResNet 100 or something like that, which are like 50 layers or 100 layers. This is only 5 layers. So there's input, image, and then there's the first convolution, which is layer 1, then subsampling layer 2, another CNN, layer 3, and then some couple of fully connected networks, and that's it. So there are only 2 convolution operations in this LeNet 5. So this is the very first one, like 1998, very old one. And then that was kind of, I'm not sure if people have noticed CNN that much when it was first proposed in 1998, because it wasn't very much of a big hit until like AlexNet came out and then swept the ImageNet challenge basically, which was back in 2012. So you also see all the famous names: Alex Krichevsky, Ilya Sutskever, who used to work at OpenAI, and again Jeff Hinton. It's a two pipeline, like it's a two-way architecture. There's like way 1 and there's like way 2. And it's a little bit more involved. So there's like more layers and more parameters. So actually AlexNet is really, really parameter heavy. Like all the ones that came after AlexNet, like InceptionNet or ResNet, they're actually more parameter efficient. And right. So this is the first. Some people think that 2012 is like the birth of like like year when deep learning was like born, basically, because at before 2012, when people tried to do image classification or visual perception, they didn't particularly heavily rely on CNN. But 2012, it was all about CNN. There's like, I think there's CNN here and also here and here. I'm not sure how many CNNs were used. I mean, I didn't study AlexNet like very carefully. It's a very old architecture. But anyway, so this was the first architecture that heavily relied on the CNN and then nothing else, no like image specific features or feature engineering of like computer vision specific feature engineering and whatnot. They didn't rely on that. They just relied on CNN and also max pooling, and some simple normalization. And I think they also used Dropout somewhere in the end. Modern combinants can do way more than just image classification. There's like image classification, retrieval, object detection, semantic segmentation, or object segmentation, and yeah, also image captioning. Also, it can go the other way around, actually, image generation. So image generation these days, people use diffusion, not CNNs, which is a little, well, so it's a mix. It's mixed between the two. And yeah, style transfer as well. So how can all this be possible? Like if you think about how a person drawing, so given an actual like photorealistic image, trying to style transfer it to like Van Gogh? Yeah, Van Gogh style, or I'm not sure what the styles are like, or this, like if you imagine a person doing this, trying to learn how to paint like this, or paint like this, or paint like this, it's going to take like several decades. No, I'm not sure, like at least like 5 years or 10 years. I'm not sure how many years it will take a person to learn, like start from nothing and then learn how to draw and then style transfer, which is a very, very like difficult technique. But modern CNNs can easily do this as long as you have enough number of images to train. Then this is easily done. So, and especially these days with the help of diffusion, I mean, this is like an easy job for machines. So let's get to the core of CNN. So if we think of basically, first of all, I'd like to note that all these following material were borrowed from Stanford's CS231N. I think it's 231N, which is a very famous computer vision deep learning class. So if you want to learn more about it, definitely go check that course out. So start with fully connected layers. So if you have, for example, assume that you have a 32 by 32 by 3 image. So this is height, and this is the width, and this is the channel, RGB, red, green, blue. So it's a 32 by 32 by 3 image. And how you would process a image like this using fully connected network is by just simply stretching it, linearizing it to 3,000 dimensions, so 3,072 dimension by 1. So it's a simply very long vector. So you don't know how to deal with this like three-dimensional images. It's like dimension 1, dimension 2, dimension 3. You don't know how to deal with three-dimensional images. So you just simply stretch it to a single long vector, and then this is your fully connected parameter. You just simply multiply it, and then you get a 10 class. Suppose that you are dealing with like 10 class classification, then you need 10 vectors, 10 dimensions out, right? So all you need is 3,000 by 10 parameter or matrix, basically, and then that's it. So if you think about what this first value means, is that you simply multiply this value or this vector with a very long, so it's 10 here, it's 3072 here, and then you have very long 3072, which is the image. So this is the input, this is the W, and you just simply multiply it, right? And then what you're basically doing is you're taking this guy, and the first column you're doing a dot product, or you're doing an inner product between the two, and that's what you get here, right? The second value here would be this vector, and the second column, and you do an inner product, and then you get the second value, right? So that's it. That's basically what's happening here, which is a little bit too simplistic, given that you're dealing with a three-dimensional data structure. So what you would like to do instead is to preserve a spatial structure. So it used to look like this, right? It used to look like this, and then there's like a human face like this. But if you linearize it or stretch it like this, then you're destroying all the spatial structures. So your human face would, I'm not sure how it would, like it would be like all like scattered around like this, something like that, right? So you don't want to do that. You want to have the original spatial structure intact, and then start processing or start extracting features out of it. So what you would do is you have something called a filter or a kernel. So some people say it's a CNN filter or CNN kernel, and it's 5 by 5 by 3 dimensionality. It has 5 by 5 by 3 dimensionality, and you do a convolution operation using this on top of this. So you convolve the filter with the image. So basically what convolving means is sliding over the image spatially and computing dot products. So what's happening here is, but by the way, before we actually see the sliding movement, this has to be the same at all the time. So this is an RGB channel, right? So if your input is three-dimensional in the end, then your filter also needs to be three-dimensional in the end, in the final dimensionality. These 5 by 5 can actually be 3 by 3, 7 by 7, it's up to you. But right now we're dealing with 5 by 5 by 3. So what's happening is you have a filter applied to this image, and I said that we're taking a dot product, right? Right here. You said we're doing a dot product. So here you have an image value. These are all pixel values. So this is like 1, 0.5, 0.7, like 0.2, 0.5. Again, like there are a bunch of like pixel values. You take those pixel values and you multiply those pixel values individually with the weights here. There are 5 weights, 5 by 5 and 3, right? So you multiply all pixel-wise values to your weights or your parameters, and then you simply multiply them and then sum them up. And basically this is the operation that we're looking for. So there's actually bias here, but we're going to sometimes omit the bias just for the sake of simplicity. Right. So what usually happens, you start from the top left, and then you slide it over to the next one. So you have, they should be overlapping with, and so this is 5 by 5, right? So it should actually look like this. So the very first one will look like this, and the second one will look like this. You're basically sliding, and then the next one looks like this. The next one looks like this. You're just sliding 1 pixel at a time, like this, and here, and here. And every time you move to a new position, you get one scalar value out. So this is a dot product, right? This is a dot product. So you should get one scalar value out. Even though you're working with 5 by 5 by 3, you're just getting one specific value out of this. So there's one scalar value, scalar value, scalar value, scalar, like all the way. And then you do it for like this. You go this way, this way, this way, this way, this way, this way. And then you get a bunch of like scalar values out. And those scalar values will be this. So simply, simply put, when you have a 32 by 30 by 3 image, and then you convolve with a 5 by 5 by 3 filters, the output size would be 28 by 28 by 1. Okay, 28 by 28 by 1. And if you use multiple filters, if you not just use, this is the blue one, right? This is the blue filter. But let's say that you have another filter, the green one, then you get another activation map right here. So one filter, one activation map, right? One filter, one activation map. So the blue one gives you one activation map. The green one gives you another activation map, and so on and so forth. So if you use 6 filters, you'll get 6 activation maps. So your output dimensionality would be 28 by 28 by 6 because you use 6 filters. So now your original image used to be 32 by 30 by 3, but after you do a one single convolution operation with 6 5 by 5 filters, your image now has a changed dimensionality, which is 28 by 28 by 6. Right, so it's a little bit spatially. It was compressed a little bit. It came from started from 32, but now we're 28. But your depth is now 3 to 6. So there's like a bit of a trade-off. Right, so one convolution, and also you can put ReLU after this. So right, if you come over all the way to here, after this, you can put a nonlinear activation function here. It could be ReLU, it could be sigmoid, it could be tanh, whichever you want, right? Right. So after convolution ReLU, you get this 28 by 28 by 6. Let's assume that you do it once again using the same 5 by 5 by, but this time 6. The innermost dimensionality has to match the input depth, right? So if this is 6, this has to be 6. So you're using 5 by 5 by 6 filter, but how many filters? You're using 10 filters now. So your output will be 10. And your spatial dimension would be, again, contracted a little bit further. So 32 to 28, 28 to 24, but your depth is 33 to 6, 6 to 10. And then it all depends on the size of your filter and how many filters you use, right? So if you keep doing this, the next one will be 20 by 20, 20 by 20, and the depth would be how many filters you use, right? So this is basically CNN, like a chained CNN, basically. So there's something called receptive field. You should be very familiar with this concept. So receptive field is at the very high, like at each layer, how like large or how many pixels a single scalar value is covering. So if you think about this first, right, this is the first input. So that your image is what? This is 8 by 8. And let's forget of the depth. It's just like a black and white image. And after first CNN operation, let's assume that you didn't contract the image space, the spatial dimension. It's just somehow you magically just used the same. You came up with the same spatial dimension, and now you're using 3 by 3 filter instead of 5 by 5. You're using 3 by 3 filter. If you're using a 3 by 3 filter, when you apply your filter here, you'll get a one scalar value out, right? Using the dot product. So it means that your scalar value here is responsible for 9 pixels. It means that this guy is looking at 9 pixels. But if you do one more CNN operation here again, then you get, again, like this guy would be responsible for this guy here. But again, if you chain it back to the very first, this guy is responsible for what? This is responsible for, I guess, like 3 by 1, 2, 3, like this much, right? Because if this guy is responsible for this, then this guy is responsible for this, and this guy is responsible for this. So this entire thing will be responsible for 5 by 5 like this, right? So a single scalar value here is actually responsible for 5 by 5 here. And if you use this logic once more, then the final third layer pixel here, or third layer single feature scalar value here is responsible for 7 by 7 here. So you can assume, you can like kind of imagine this guy looking at 7 by 7 receptive, 7 by 7 pixel, which we call a receptive field. So your receptive field will get larger and larger as you apply more convolutional layers. So it's basically, like linearly increasing. This guy was looking at 3 by 3. This guy's looking at 5 by 5. This guy's looking at 7 by 7, right? So that's why as you move up, you can start to like understand higher level features like human face. Instead of this scalar value can only look at one like small patch, which is responsible for like edges or shapes or texture. But if you go this way high up, then you can see the entire picture, which you can also look, you can start looking at human face with like eyes and like nose and mouth, something like that. Right, so there's a trend. This is also a very important concept, because if you wanted to look at the 7 by 7 pixel from just using one convolutional layer, you would require a single 7 by 7 filter, right? A single 7 by 7 filter would give you a 7 by 7 receptive field right from the first layer. But then you would require 49 parameters because it's a 7 by 7 filter. But if you use three by 3 filters, so 3 times 1, 2, 3, 3 times of 3 by 3 filters, which would require you how many parameters? It would require 27 parameters only. So using using a smaller number of parameters, 3 layers of 3 by 3, which is 27. Let me write it down here. 27 here and 49 here. Using a smaller number of parameters, you're still getting 7 by 7 receptive field in the end. Of course, you would have like 3 layers. So you require some back propagation, but still, like you're getting way more efficient. You're getting the same job done way more efficiently. So that's the beauty of stacking more layers. Yeah, the 4 requires less parameter and deeper. So deeper. Also, having to do more back propagation seems like a bad thing, but as I said in the was it the autoencoder class? Having more layers gives you a chance to warp or distort your space more, basically, more frequently or more times. Basically, you have 3 more times to warp your space, which is all about nonlinear activation function, right? You saw like how linear activation the linear operation gives you like the rotation and the expansion or compression of the space, but only when you have a nonlinear activation, you can start like warping or distorting your latent space like S shape when you are using sigmoid function, right? The same thing happens here. When you're using ReLU, you are warping your space 3 times, getting more expressiveness out of this. All right, moving on. So you can visualize your learned kernels. So there are how many kernels? There's like 1, 2, 4, 5, 6, 7, 8. So this is a VGG16 model, and I guess it's using 64 kernels in the first layer, again 64 kernels in the third layer, and something like that, I guess. So you can see that each kernel is paying attention to different stuff. Like some kernel is responsible for only like looking at yellow color or green color or blue color. Some kernel is only is paying attention to like vertical lines or horizontal lines or diagonal lines, something like that. So very low level features. But if you start going up like the higher level here, I guess it's hard to imagine what it is doing. Yeah. I guess this is a little bit more intuitive. If you look at like this high level feature here, it's I think this one is a little bit more intuitive. So this guy is somewhere in here in the kernel, it is looking for like orange features, and there is an orange feature in the original image, right? So its activation map would look like this. So where there is orange feature, it has a higher activation, like white activation. And where there is no orange feature, it's usually like dark or gray, right? So you can see like these features, or I'm sorry, these filters, each of them have a specific purpose. And the activation map of these filters or these kernels would actually look like what they're actually looking for. So you can see that the activation maps all here, they all have like it has different outputs. And when you combine all of them together, you can finally understand that you're looking at a headlight of a car. So a typical so convolutional neural network, CNN architecture looks like this. So there's an input image, and you do some convolution, nonlinear activation, convolution, nonlinear activation, and sometimes you slide in a couple of like pooling operations here and there, and then you do again a convolution, convert value, again pull, convert value, pull, and then finally you do a classification, whatever classification you are trying to do, whether it's a MNIST digit classification or ImageNet 1000 class classification. It's all up to the task. So we're going to talk about the pull operation. Not now. Okay. So some number of slides later. All right. A little bit more on the CNN. So we've seen this when you have 32 by 32 by 3. When you apply 5 by 5 by 3 filter, you get one activation map out with 28 by 1 dimensionality. Yeah. When you slide from the start like this using, let's assume the 3 by 3 filter, you slide from the left top, you move one pixel to the right, again, 1 pixel to the right. You moved how many times? You moved 5 times because you started from here and you moved 1, 2, 3, 4, 5, and now you're here, right? So you moved 5 times, and it's the same with the vertical. This was horizontal movement. The vertical movement would be the same. You would move from 1, 2, 3, 4, 5. So it's 5 times. So it's 5 by 5 out. That is why you get a 5 by 5 output. So that's why you get a little bit compressed output spatial dimensionality. You started from 7 by 7, but now you get 5 by 5 out. And yeah. So, and actually, yeah, this is even more pronounced if you use stride 2. Stride means how many pixels you want to move horizontally or vertically. So if you stride 2, you started from here, but the next one you're here. You're jumping 2 pixels, right? So you move from here to here, and there are 2 pixels difference compared to how you move from here to here, which is only 1 pixel difference. So stride 2, you can move how many times with stride 2? Only 3 times. You can only move 3 times vertically and horizontally. That's why you get 3 by 3 output when you use stride 2. So stride 2 would give you further compression of your original image. If you use stride 3, how many times can you move? 1 and 2 and not 3. 1 and 2 and not 3. It doesn't fit. You can't move 3 times. You can't. There is like a space left. There with stride 2 you cover this much and this much, and you're not covering this. So you're missing this information, which doesn't work. So it doesn't fit. So you cannot apply 3 by 3 filter on a 7 by 7 input with stride 3. So there's a bit of a problem. So what you can do is actually, there's like a bit of a simple equation. What's the output size of your convolution operation? So this is your original pixel size, n would be 7 here, and this is your filter size 3, and your stride, sometimes it's 1, sometimes it's 2, sometimes 3. When you use 3, it doesn't work. Only when you use 1 or 2, you get an integer point out. So this is a simple operation that you can use. But what you can do is actually, you can do some padding. If you don't want to compress your image while doing a convolution operation, you can pad your image like this. So you just zero pad your image. And then when you zero pad your 7 by 7 image, it would be what? It would be 9 by 9. It would be 9 by 9, right? And then you start doing convolution with 3 by 3 filter. Then how many times can you move horizontally and vertically? You can move 7 times, like 1, 2, 3, 4, 5, 6, 7. You can move 7 times. So your output would be the same. Your output dimensionality would be the same as the input dimensionality before the padding, of course. So this was your original image. This is your padded image. But your output would be, again, 7 by 7, according to this equation, because now it's 9 minus 3 divided by stride, and then plus 1, which is what? Which is 7. So when you use padding, you can preserve your spatial dimensionality, right? It's the same thing. Oh, and if you're using stride 2, for example, if you're using stride 2, then you would want to use larger padding, or vice versa, or in the same manner. If you use larger filter, instead of 3 by 3, you're using 5 by 5. Then again, you need to use a larger padding. You need 0 pad. You need to have like 2 pads, like here, like you need to have another pad, like right around here, surrounding the first pad, so that you can use 5 by 5 filter and still get 7 by 7 out. If you use 7 by 7 filter, you need like 3 pads, so on and so forth. Same goes with stride. Same goes with stride. If you want to stride like 2, if you want to use stride 2, you need like more pads as well. So, like using padding, you can always have your spatial dimensionality preserved as you move up the convolution operations, right? So example, if you have input volume 3 by 30, 2 by 30, 2 by 3, and you have 10 5 by 5 filters with stride 1 and pad 2, what will be the output volume size? You can, before moving to the next page, you can try to calculate it in your head. And there's a bit of missing out information. It should be actually 5 by 5 by 3 filter, because this has to match. This 3 and this 3 has to match, right? So your activation map would be what? So you have stride 1 and pad 2. So actually, oh, you're using 5 by 5 filter with pad 2. So your spatial dimensionality would be preserved. And then you have 10 filters in action. So it would be what? It would be 32 by 32 by 10. Your output volume, or your activation map, would be 32 by 32 by 10 and 32 by 32 by 10. So far so good. You should be able to calculate this in your head. And if there are anyone who can't understand what's going on, you can raise your hand or ask me a question like why would we get this? Like, does anyone, like, is there anybody who doesn't understand this process? When you have 32 by 32 by 3, you want to convolve with 10 5 by 5 filters with stride 1 and pad 2, you would get this activation dimensionality out. Is there anyone who doesn't understand this? No one. Okay, that's good then. So how many parameters are we using when we went from this to here? We use 10 by 5 by 5, 10 filters, where individual filter has a dimensionality of 5 by 5 by 3, right? So that's 75 times 10. So the CNN filters alone would have 750 parameters, and you would also have to account for the bias vectors. So it would be what? There are 10 filters. So it would be 10 bias is it 10 bias variable? The 10 bias parameters. So it will be 760. Am I right? Yep, 760. So again, if you don't know what's going on, you can raise your hand. Right. So what kind of, regardless of which library you use, whether you use PyTorch or JAX or what. I don't think JAX has CNN. I'm not sure. PyTorch or TensorFlow or whatever. Like, there's a lot of libraries out there. Whichever you use, when you're using CNN, it would always accept the same, like, parameters, which is what is your height, width, and height, and input channel, and what kind of how many filters you want to use, what's the filter size. So this will be 10, this was 5 by 5, and how many strides, and what's a pad, how many like pads do you want on your original image. Like, these KFS and PFSP is always universally used when we're dealing with CNNs. Oh, question. What is bias there? Bias is what is bias? Yes, that's a very fundamental question. We're talking about this bias. when you have a linear layer or linear transformation layer, you all usually have a parameter and a bias, right? That this is the bias. Right. +1 bias. Another question. When it comes to calculating parameter numbers, the input channel is not considered. Input volume 3 in the input channel is considered because actually, as I said, it should be a 5 by 5 by 3 filter. So these two have to match, right? So input channel is considered. So it's 5 by 5 by 5 times 5 times 3 is 75, and there are 10 filters, so it's 750. And then there are 10 biases because there are 10 filters, so it's all in total 760. Does that answer your question? All right, cool. All right, moving on. Oh, it's a one by one convolution. So what we used so far was either like 5 by 5 or 3 by 3. Like this was 5 by 5 filter. We also talked about 3 by 3 filters. Sometimes people use 1 by 1 filter, which is actually focusing on 1 pixel at a time. So 3 by 3 filter will focus on 9 pixels at a time. 5 by 5 filters will focus on 25 pixels at a time, right? 1 by 1 focuses on only 1 pixel at a time. So basically what 1 by 1, if you imagine a 1 by 1 convolutional 1 by 1 filter, just like here, I think I could draw a little bit better. Like this. So there's only 1 pixel here, right? And it is moving around like this. And what's happening is especially let's assume that you're using 32 filters. So the input is 64, so there's like hidden information, which is 1 by 1 by 1 by 1 by 1 by 64. And you're using 32 of them. So your output would be actually smaller. Your output depth would be smaller than your input depth. So what's happening here is basically you're just compressing only the depth. You're not meddling with the spatial dimensionality whatsoever. It's 56 to 56 because you're handling only 1 pixel at a time. So it's 56 here, 56 here, but you are using less number of filters than the input channel. So it's 32. So basically you just compress the depth, and that's it. You didn't meddle with the spatial dimension. You only compress the depth. So if you want to do this kind of operation, 1 by 1 conv is what you are looking for. So that's a special kind of a filter. Right. Oh yeah, I've already drew this, so we can move on. Question, is this regarded as downsampling on image? Actually, no. Downsampling, we're going to talk about downsampling, which is basically pooling is kind of a downsampling. You can well, it is a compression, but I wouldn't call that a downsampling. So when you're using conv2d API in the PyTorch library, you need to specify at least these four, 1, 2, 3, 4. The how many filters, size of the filters, stride, and padding. So it's here, channel in channel, and then so this would be what's the depth of your input channel, input image. If it's RGB, it would be 3, right? Output channel is the how many filters you want to use. Kernel size is like 3 by 3 or 5 by 5. Stride is on default set to 1. Padding default set to 0. And there are some other like more like auxiliary arguments where you can do like dilated CNN or like group CNN, what yada yada. But basically the must parameter or argument you need to set is at least these 1, 2, 3. How many the input channel, the output channel, which is the number of filters, and the kernel size. All right, moving on. And I would assume that the API would look very similar in all different kinds of like deep learning library, TensorFlow, TensorFlow 2, PyTorch, whatever. And then we come to pooling. So several like slides ago, there was let's like here. there were some pooling operations here and there, right? So we're going to talk about what pooling is. Pooling. So pooling is a downsampling operation. So if you have a feature map or activation map that has the dimensionality of 20, 2 to 4, 2 to 4, 64, when you do a pooling operation, you would like to have an output like this, right? Output like this, which the channel hasn't changed. Only the spatial dimension is halved, right? So you want to basically pooling is trying to compress your spatial dimensionality and don't touch the depth, right? And you pull and also what you want to do is you want to be able to do this kind of compression without any learnable parameters. So the simplest thing you can do is actually max pooling. So max pooling with 2x2 filters and stride 2. So 2x2 filter. So let's assume that your input image was 4x4, and let's forget of the depth, right? Let's assume this is black and white image. It's a 4x4 image, and you want to compress it to 2x2. And how you would do it is by using a max pooling operation where you're using 2x2 filters, so you're looking at 2 pixels at a time, and your stride is 2. So when you are done with this, you move to here, and then you move to here. And at each position, what's happening is out of these 4 pixel values or out of these 4 feature values, you're taking the maximum value out. So it would be 6 here. So you get 6 out. And in the next position, you have the 8, which is the maximum value in these 4 pixels. So you get 8 out. And then you get 3 out, you get 4 out. So that's how you get 6834. So you've downsampled your image actually you've halved your image. So it used to be 4x4, now it's 2x2, and you're still retaining the strongest signals in each patch, right? So basically what pooling is doing is you want to only retain the strongest signals in local region or in this neighborhood. You can do max pooling, or you can do also average pooling. Some people use average pooling, right? And it will be exactly what it says. You just simply sum them up and then divide by 4. Sum them up, divide by 4, sum them up, divide by 4, sum them up, divide by 4. But I think max pooling is way more frequently used than average pooling because it's all about signals in the end. You want to deal with pixel signals, and then you want to make you want to do classification, object detection, or whatever. And usually it's the strength of the signal that really matters. So this has nothing to do with any learnable parameters, right? Because this is all rule-based. You're just looking at 4 pixels and taking the maximum value out, then move to the next position, take the maximum value out. So there's nothing to learn or anything. It's all like hard-coded. So it's a very cheap operation. Right, so that's why you sometimes use pooling operations here and there to drastically compress your spatial dimension. Because if you start with a very large, like 128 by 128, and then you keep using convolution with padding, then you're not compressing your spatial image at all. And your input depth would keep increasing because you're using like 10 filters here, 20 filters here, 30 filters, 40 filters. If you're using like more and more filters, you're increasing your dimensionality of your activation map you're at least increasing the channel and you're not decreasing the spatial depth, the spatial dimensionality. So that's why you want to use pooling operation here and there to sometimes have and then have and then have. So if you started with, for example, here, if you started with 128 by 3, then at some point in the end, what you would like to have is like, I don't know, like 16 by 16 by 64, something like that. So you want to compress. If you started with what's the dimensionality? Like 128 by 120, 16K, 48K. So it's used to be 48K. And if you multiply this, what do you get? It's 256, 2 to the 8, 2 to the 6, 2 to the 14, 2 to the 14, that's what? 16,000? Am I right? Is it 16,000? Yeah, 16,000. Let's just assume this 16,000. Basically, so you've like while increasing your channel depth or the semantic layer, you're compressing your spatial layer, and in the end, you would like to have make an informed decision, and that's usually how CNN works. So you compress your spatial dimension and you increase your channel depth. You can go even like drastically further. You can like go further and make it to like 4x4 by 64. Then you would compressing it more, and then basically that's what you would be doing. So in order to do this, you need pooling operations here and there, because if you want to compress your 128 by 128 all the way to like 4, then you need to have like too many like convolution layers. Right. So the summary is convnet is stack of or repeated layers of convolution and also non-activation layer, pooling, and then the final final fully connected layer to make a classification. And these are a little bit like old, not old, but pretty much like dated insight. Trending towards smaller filters and deeper architecture. This used to be true, but these days people usually use like transformers to deal with images. So like these kinds of like well-known insights are no longer like I mean, if you want to use CNN, you should keep this in mind. But these days, CNN is kind of like an old architecture by itself. Yeah, and the trend is towards getting rid of pooling and FC layer. So if you like, some people might ask, like, if you remove pooling layer, how would you compress your spatial dimension learning? Actually, you can use stride. So if you use stride 2 or stride 3, you can drastically compress your spatial dimension again. So you can use either stride or pool to handle your metal to like play with your spatial dimensionality. So yeah, the trend is towards getting rid of pooling and fully connected layer as well. Right. Moving on. So there's also 1D conv. 1D conv is easier than 2D conv. It's just, let's assume that you have a sequence of features instead of like 2D patch or two-dimensional features. You have only one-dimensional feature, which could be like time series data or like text for that matter. And you would use a 3x1 filter, I guess, because it's no longer 3x3 because you're using one-dimensional input. So it's just filter size of 3 and stride 1. So you would move 1 pixel at a time. If you stride 2, you would move 2 pixels at a time. So the first position would be looking at 3 filters, and then you move 2 times, 2 pixels. You would move it, like you would look at this, and you would look at this, and so on and so forth, right? So again, if you look at this, you are compressing a 7-dimensional input to 5-dimensional input. If you look at this part, you're compressing 7-dimensional input into 3-dimensional output using stride 2. So that's what I said about if using stride, you can replace pooling operation. So the very first attempt to use 1D convolutional operation on text is by Yoon Kim from, well, who's now an MIT professor now, but this is like way back, like 10 years ago. So Yoon Kim used 1D convolutional operation on text to do, I think it was document segmentation, no, or like topic classification or something, or sentence classification. So you have a word vectors, like wait for the audio and don't rent it. So each word is a vector. We'll talk about word vector in class 8 or class 9. So it's don't worry if you don't understand what's going on. Just we'll learn about it in like couple weeks later. So there's a sequence of word vectors. So you can think of this as a multivariate time series. So there's dimension 1. So this is a time series. This is a second dimension time series, third dimension time series. So it's a multivariate time series data. And given a multivariate time series data, you can use 1D conv to compress it or process it, and then finally get some output out, right? So that's the whole idea. You can also have 3D convolution, 3D convolution as well. If you are dealing with 3-dimensional spatial image, such as like videos, where the third dimension would be time, or CT scans, which is actually a true 3-dimensional image, like MRI or CT scans, you can use 3D conv. And 3D conv would require exponentially more increased number of operations, because you need to move this way and this way and this way, right? So you have one more axis. So you need to like move 3, like you need to move all the way here and all the way here and all the way here as well, right? So it's very computation heavy. Yeah. So 2D versus 3D, it's basically 2D, you move for like this. 3D, you move like this, and then go to next one, and go to, well, actually not next one, because you need like three-dimensional filters. So it's, you're moving like just like it says, like here. So it's a very, I don't think people use 3D convolution very heavily because of the number of sheer computation you need to do. And if you use like transformer, I guess you can do a little bit more efficiently. Or you can do a hybrid between CNN and transformer as well. Some people do that. So we'll talk about that when we learn transformer. Right. So this is basically it about like convolution, and we've like learned convolution, strides and pads and whatnot, and the receptive field. Then we moved on to like the 1D conv and 3D conv, and now we're basically done with the convolution, the concept of convolution. Now we're moving on to BatchNorm and Dropout. So, any questions so far? If not, then we can move on to BatchNorm. So, I'm guessing that most of you are already familiar with normalization, like Z normalization, where you transform your input features to follow this distribution. Basically, what you do is you have your original input, you have your original feature, you subtract the mean of the features, and you divide by the standard deviation, right? So basically, that's when you assume that your features follow a normal distribution, you can do a Z normalization like this. So that's a popular technique, right? And machine learning, when you deal with like different data, like MNIST or CFAR10, there's something called the distribution shift. So when you train your data, when you train your model on here and then you test it on here, it will not work well because the distribution would be different. This is all like digits, like 1, 2, 3, 4, 5, 6, 7. And Cypher 10 is like bird or car or airplane. So completely different stuff. So when you train your model on on digits, numbers, and try to classify birds or planes, it's not gonna work. So there's something called this is something called distribution shift. Your training distribution and your test distribution is vastly different. And machine learning models are very vulnerable. It doesn't handle distribution shift very well. Still, it is can't. Basically, it's really hard to handle distribution shift. And this kind of distribution shift actually happens internally inside a model, which is we call a internal distribution shift. And this is what motivated batch normalization. There's a question. If my image has, for example, 640 by 480 pixels, then do I have to crop it to n by n images? So you're asking whether you need to make it into square, right? Like 640 by 640 by padding, or 480 by 480 by cropping. No, not really. So modern CNN architectures, well, actually, we need to talk about here. Trends towards getting rid of pool and FC. I've talked about why we can get rid of pool, because we can replace that with stride, right? Also, getting rid of FC layers actually lets you, getting rid of SFC layers frees you from having to have a specific input dimension of your image. So if you if you don't use FC layer anywhere, I mean, at the very end, you need still FC layer because you need to have a classification layer, right? If you're dealing with MNIST images, you need to have a 10 dimension out. If you're dealing with image classification, ImageNet, you need to have 1,000 dimension out. So in that sense, you need at least one FC layer at the end. But before that, if you don't have any FC layer anywhere, then you don't need to care about your input dimensionality. It could be 128 by 128, it could be 64 by 64, it could be 64 by 128. Doesn't really matter, because all you're left with is convolution and pooling. Or if you also get rid of pooling, it still doesn't matter. If all you have is convolution layer, convolution doesn't depend on your spatial dimensionality. So you can deal with any kinds of any size of image. And at the very end, you use something called like global average pooling, which we can talk about in the ResNet. So if you have only convolutions and one global average pooling layer at the end, your image size or your spatial image spatial dimensionality doesn't matter. So you don't have to crop if you stick to that principle. If this principle being only using convolution and no FC layer in between. Like if you use like FC layer here and here and here, then you need to stick to the same image size as when you trained and when you're doing test. You can't change your image size, but when you're using only convolute, then you can change your it's okay to change your image spatial dimensionality between training time and test time. So hopefully that answers your question. Okay, so we were talking about internal distribution shift. So distribution shift is usually when we talk about distribution, we're talking about when training distribution and test distributions differ, but inside it also happens. So if you imagine a multi-layer deep learning network, it could be like CNN, FC, fully connected layer, doesn't matter. It's just, there are like a bunch of layers here and here and here. And you're looking at one, no, actually two layers, like layer K-1 and layer K. So what's happening here is that layer K-1, so the previous layer's output is the next layer's input, obviously, right? So previous layer's output, if it has a certain, if the previous layer's output follows a certain distribution, it could be this, it could be this, it could be this, it follows a certain distribution, then the input to that layer, the layer K would perceive this specific distribution as an input to itself, right? But when you're doing back propagation, starting from like to the top, from the top to the bottom, this layer will have changed its parameters, and because of change parameter, the output distribution would change. Let's, for example, before the parameter update, it used to follow this distribution, but after the parameter update in this layer, now it's following this distribution. So this layer doesn't know that this distribution has changed this distribution, because this guy has already updated its parameter, and this guy is completely oblivious to what's happening in down here. It doesn't know. It has no idea. So it would not know that the distribution of this output from here has changed from this guy to this guy. And in the next iteration, next mini batch iteration, this guy would have to adapt to the new distribution, which would be a waste of optimization process. If the output distribution from this layer was always this, then this layer's job would be way easier than having to adapt to dynamically changing distribution, right? So that's the whole idea. This layer K-1's output changing from this guy to this guy to this guy at each mini batch update is called internal distribution shift. Or the BatchNorm paper calls this internal covariance shift, but it's the same thing. So what we would like to do is we want to normalize the output of the previous layer to a specific distribution, hopefully this, so that the next layer will always handle the same distribution over and over again, right? So that the whole training process would be way, way simplified. So the way you do it is batch normalization has two learnable parameters, gamma and beta. So what's happening is, first of all, you calculate the batch-wise mu. So you have mini batch, right? So you calculate all the samples in your mini batch, and then you calculate the mu and the sigma standard deviation, and then you do the simple z normalization, and you put some epsilon in, because sometimes your standard deviation could be too small, then this whole value would blow up, right? So you have some buffer to handle that. So there's epsilon here, but basically this is a z normalization. After z normalization, you scale and shift your normalized value to get the final value out. So for example, so the paper was worried that this kind of z normalization would be too harsh of a manipulation of your feature. So it stretches and translates, basically. It scales and shifts to some other value so that it would be like more manageable for the next layer to handle. So these two values, gamma and beta, are learnable. And all the other, these operations are just, hard-coded, right? So that's what BatchNorm is. So you would get, for example, like regardless of what the internal parameter update gives you, like this kind, like the various distribution, you always want to scale and shift and like manipulate into this particular distribution so that your layer K would always look at this, right? So that's the whole idea. Basically fixing the distribution of the internal layers activation. That's the whole idea. So when you're dealing with fully connected network, there's like n number of features in your, n number of samples in your mini batch, and each sample has like d dimensionality. So you can think of this as a fully connected network. So it's like row by row, it's a different sample, right? So what happens in batch normalization is you have batch norm per dimension, per feature. So this first feature, there are n number of features because it's the size of the sample is n, right? So there's n number of features in the first dimension. So you have mu here, there's mu here, and there's standard deviation here as well. So there's like one pair of mu and standard deviation per dimension, and then you apply that to each individual features here, right here. You're doing a z normalization per individual features per sample here. This is what's happening here, and then you scale and shift. Do we have a scale and shift? Yeah, I mean, yeah, there's scale and shift. So this is the reason for having a scale and shift is exactly this question. What if zero min unit variance is too hard of a constraint? Like having enforcing this kind of z normalization on every feature could be too hard of a constraint, could be a harsh manipulation. So you want to relax it a little bit. So that's where, why is that working? Okay, that is where scale and shift comes in. So you're relaxing the manipulation a little bit. So you've taken the mu out and then you've divided by the standard deviation. If that seems too harsh, then you scale it back and then shift it a little bit. So, and how much you want to scale it, how much you want to shift, that's learnable. It's a learnable parameter. It's just this is optimized to just lower the objective function of your model. So if somehow this gamma turned out to be learned like sigma value, and somehow this beta learned the mu value, then this will be exactly the identity function. So that's, at least there's like some room for like identity function. Right, so this is it. So yeah, and the downside or the drawback of batch normalization is these values mu and sigma depend on the mini batch. Like what kind of samples happen to be inside the mini batch decides this mu and sigma. So this is an estimate depend on mini batch. So that you can't do that at test time. At test time, you usually handle one sample at a time, right? You don't sample a batch of test samples. You handle one sample at a time. So that's why you cannot estimate these mu and sigma values because there's no mini batch when running a test. So that's why you have to do a running average. So when you're training your model, you keep all the mu values or the sigma values as you train your mini batch after mini batch. You do a running average and you keep them around. You keep these mu and sigma around so that you can use it at test time when there is no mini batch. So that's kind of this is a very like a easy mistake you can do when coding. So when writing like PyTorch function or like TensorFlow function, when you're using BatchNorm, this kind of operation always is a problem because your training environment and your test environment is vastly different. And you have to keep certain values during training and then save them and then apply them in the test. This is like an easy, like a very, becomes, yeah. Oh, yeah. Oh, I'm sorry. I think I explicitly said that these values are the cause of often being a cause of a bug or a coding mistake or coding problem. Yeah. But I guess I lost it somewhere. Anyway, so you have to really keep that in mind. BatchNorm, if you use BatchNorm, your training and testing environment is different. So that's often the cause of a bug or a problem. So you have to keep a very careful attention to the details. And where you would use batch norm, like is it after the fully connected layer or is it after the nonlinear activation layer? It's topic of debate. Yeah, and I think people, yeah, as it says, usually people use it before the nonlinear activation function, but I think personally, I think there's no like gold answer here. It could be anywhere. Oh, this is behaves differently during training and testing. This is a very common source of bugs. Yeah, keep this in mind. So that's why some people don't like to use batch norm and they just use layer norm and that's it. Because layer norm, we're going to talk about this. Layer norm doesn't care about it doesn't require you to pay attention to difference. There's no difference between like training and testing. Layer norm is just easy. So some people just prefer layer norm for those reasons. Right, so the batch norm, the lesson is makes the deep networks much easier to train because you've handled the internal distribution shift. So there's like very minimized internal you can't say that there's zero internal distribution shift because that's impossible. But you've like you've minimized the internal distribution shift so that the layers are easy to handle like one after another, right? So it improves the gradient flow, allows higher learning rate, and faster convergence, like all good. So batch norm for convnet, I'm sorry, batch norm for fully connected net is what we looked at right here. Here. Like this is a fully connected network. So it's a batch norm for FC, but batch norm for convnet is a little bit different. So batch norm for convnet is here we've averaged over the sample, the mini batch access, right? So there's like n number of samples. So we averaged the sample, we did a sample wise average. So you've got mu and sigma for each dimension, right? In ConvNet, you average across sample and also height and width so that your mu and sigma, you have one mu and sigma per channel being the dimension, channel being the feature dimension, right? So you have one mu and one sigma per channel, and then your gamma and beta values will also have, you will also learn them per channel. So that's it. So this is batch norm for ConvNet. You average over n and height and width, and you leave the channel intact. When it comes to layer norm, so layer norm is something that came up in 2016 by, again, like Jeffrey Hinton and their lab. And it's, if I remember correctly, it was designed to handle RNN's internal distribution shift. So batch norm cannot handle RNN. You cannot apply batch norm inside RNN because there's like a loop structure, but layer norm can be used for RNN. Specifically, it was designed for RNN actually. And you can see that it's averaging over channel dimension, not sample dimension. So batch norm averages over the batch dimension or the sample dimension and leaves the D intact. But layer norm is different. Layer norm is vice versa. Layer norm, you average over D so that there's mu and sigma for each sample. There's mu and sigma for each dimension, but in layer norm, there's mu and sigma for each sample, and that is why you don't need to have a running average over mu and sigma because your mu and sigma doesn't depend on your mini batch. It depends on your channel, and this is fixed because this is your model architecture. So you don't need to have a running average over mu and sigma, and there's no different behavior between training and testing. So it's way easier to code, and there's no like source of bug or anything. So layer norm has that kind of philosophy. There's something also called a instance normalization. So if you're familiar with like StyleGAN, it uses something called adaptive instance normalization. And if you do like a style injection, there's also instance normalization. So if you're into that kind of stuff, then you should be already familiar with that. So in batch norm, we've averaged over n and spatial dimension and left the channel dimension intact. In instance normalization, you don't you don't average over samples. You only average over spatial dimensions, and you leave the channel and sample dimension intact. So there's like mu and sigma for each sample and channel. So that is why it's called instance normalization, because you have each instance intact. You have mu and sigma for each instance. Here, you have mu and sigma for each channel only, but now instance is preserved. So that is why it's called instance normalization. And again, it's same behavior at train and test because your height and width doesn't change during before and after training, right? So it's again easier to code. So if you visualize it, this is the batch. So your image would have height and width and channel, but we cannot draw four-dimensional structures in reality. So this we just collapsed the height and width into a single axis here. There's channel axis here, then there's sample axis here. So batch norm normalizes this much. I mean, sorry, averages this much, right? So averaging over sample dimension and also spatial dimension, and you leave the channel intact. Layer norm is the other way around. It leaves the samples alone and only averages over channel and height and width. Instance norm only averages over height and width, like height and width, right? Here. So these are the differences between different normalization techniques. Okay, I think we can move on to the dropout. So dropout is a very old technique. I'm not sure if it's still like heavily used. I'm not sure if dropout is now so popularized that just people use it without noticing. Like it's in every piece of code that you write in PyTorch automatically, or whether they just don't use it. I'm not really sure which is the reality. But it used to be a very big thing back in 2014, 2015, 2016. Like dropout was an explicit technique you would use to have your model better generalized to test distribution. So what's the simple? This is a very simple idea. You have like multiple layers of multiple layers of neural networks, and you would zero out a certain percentage of hidden of nodes in each layer. So for example, if you don't use dropout, this is fully connected network, right? If you use dropout, then on average, like I guess this is like 40%. I guess the P is 40% here. So you would basically drop out certain percentage or certain portion of hidden nodes in each layer, so that you would only have to rely on active layers, like active layer. So it would constraining your model to have like lesser expressivity to handle your task. And it's kind of like it's a very strong type of regularization. If you remember regularization way back in, I think it was week 2 or week 3. If you remember regularization, it was to constrain the freedom of the parameters. Because if you have like too large value of parameter, your regression would look like this, right? Having a large magnitude parameter would enable your model to behave very weirdly like this. So you would constrain your parameter to only take small magnitude values. So your regression would look nicely like this, right? It's the same thing. You are constraining your model's expressivity to behave in a certain like well-managed way, but it's just way harsher than like L2 regularization, because you're basically dropping out nodes from time to time. So if you're using dropout in convnet, what you would do is there are different ways to apply dropout in convnet. You can drop out activation maps. Basically, for example, when you're sliding over this input map, you would have scalar values generated from the input, right? From the convolution operation. And sometimes you would zero out certain percentage of the activation features. You can do this, or you can zero out the entire activation map, because you're using multiple activation maps. If you're using 6 filters, then you will have 6 output, and you would zero out the entire activation map, like based on some percentage. So this is another way to do it. So it's up to you what kind of dropout you want to use. And this worked surprisingly well back in 2014. I think dropout was proposed back in 2013 or 2014. It used surprisingly well. So even when you use like a little bit of a like too large of a model, if you use dropout, then it would behave like a smaller model, because you're dropping out parameters completely, right? So it's a very strong form of regularization. All right, so yeah, we are running out of time, so I guess we'll have to like skim through the CNN architectures. Any question regarding batch normalization and dropout before we move on to the CNN architectures? If not, okay. So then let's look at all the. This is a starting from 2010 to 2017 ImageNet challenge. So ImageNet challenge is you need to classify an image into 1,000 different classes. So it's a very fine-grained labels, like some breeds of a bird or like some types of animals, like or different types of cars or something. It's a very fine-grained, very challenging data set. And before the rise of deep learning, which is 2012, this was what people used to get, like 28% error or 25% error. So error meaning it's basically like 72% accuracy, 75% accuracy and whatnot. But then after 2012, after like CNN deep learning architecture came in, it started decreasing very rapidly. And 2017 is using some SCNet. I'm not sure what SCNet is. But basically ResNet, again, I mean, ResNet already achieved like 3.6 error, which is like 97% accuracy, where human accuracy is 95. So we've easily surpassed human performance in 3 years since 2012. It only took 3 years to surpass human performance. Before it was like nowhere even close. So you can see the power of deep learning. And the very famous architectures are like these ones, the ZFNet and VGGNet and InceptionNet and ResNet. These were all like very famous. And I think we may have some time to look at only like one or two of them. So AlexNet, it's complex. It looks a little bit complex because it has like two routes, and it uses fully connected layer like heavily. Like there's fully connected layer here and here and here. So the total number of parameters is pretty large. Actually, I'm not sure if I've written it somewhere here. Maybe not. But it uses like millions of parameters. It's not a very parameter efficient architecture. And then came VGNet, which is this is a typical architecture that we talked about. There's like some conv and pool, conv and pool, conv and pool, conv and pool. And there are a series of FC layers again, just like this, like series of FC layers here. There's a series of FC layers here. So this is not like image like size agnostic or size generalizable because of the fully connected layer. And then after this, oh, so the reason that people like came up with after this, they came up with this idea is because they wanted to use came up with this is they wanted to use like deeper networks. So you can see the size of the filter is pretty large, like 11 by 11. Like people don't use 11 by 11 filter these days. Like this is a very old idea. So instead of using large filters, VGNet use only small filters, only 3 by 3. And stacking them up, you would have the same receptive field size and also smaller number of parameters. So this embraces that idea. And then after that came LUNet, I mean GoogleNet or InceptionNet. So InceptionNet, the reason that it's called InceptionNet is because it's using this something called Inception module repeatedly. There's the Inception module here, 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 here. So it's kind of like reusing the same module multiple times. So this didn't used to be the case because you can see here like two layers here, two layers, 2, 3, 3, 3. So it's a little bit like arbitrary. Like why would you use 2 here and 4 here? It's a little bit like a designer's choice. But here you have a well-defined, well-designed like Lego block basically, and then you're using that block repeatedly here, and it gives you a pretty good performance. So that's the idea of Inception. And there is like one by one convolution used here. So where you compress the channel dimension, right? And then yeah, moving on to yeah, you can think of this as like a story time. I don't think I have time to like look at the specific architectures. If you're interested, you can check out the slides later, or you can actually read the paper, the Inception net. Moving on, now we have 22 layers. So the number of layers is being increased as we move in time, like 2012, 2013, 2014, and we come to ResNet. So ResNet is the first model. In my opinion, it's a personal opinion. I think ResNet is one of the papers that changed the landscape of deep learning. Basically, some like rarely an idea survives over time. Like There, like, as I said, like millions of papers come out every day about like deep learning and neural network and machine learning. Rarely an idea survives over 10 years of time or 10 years of development. And those ideas are attention, which we're going to talk about, residual connection, and maybe variational autoencoder, maybe that as well. And basically, like what ResNet is one of them, in my opinion. ResNet is something that fundamentally changed the practice of deep learning. And why did it change? It's the ResNet is the first model that was able to stack more than 100 layers. Before that, before ResNet, 22 layer was the maximum. 22 or well, how deep was VGG? It was like 16, 19. AlexNet was, I think it was like 12, something like that. But these were like the state of the art before ResNet. But ResNet came out and then it showed that it was possible to stack more than 100 layers. And how did it do that? It was by using residual connections. So let's talk about that. So the idea is it's a very nice paper in that it focuses on a fundamental problem of optimization. So when training a stacked CNN model, 20 layer versus 56 layers, so it's 20 layer CNN, it's a 56 layer CNN, training error for 56 layer, the larger or the deeper CNN model has a larger training error and also larger test error. So it's not overfitting problem. That's what the authors of ResNet thought about. If it's an overfitting problem, then your training error would be lower, but your testing error would be higher. That's the overfitting, right? Overfitting was when you're using too large model, too expressive a model, you can overfit to your training samples and then work and perform poorly on testing samples, right? But that's not the case here because larger model or the more expressive model is showing higher training error and higher testing error. So this is not an overfitting problem. This is not overfit. It's not caused by overfitting. It's an optimization problem. That's what the authors of ResNet thought about. Because if you use a larger model, you should be able to overfit or at least memorize your training samples, but that's not the case. So there's something going on with the optimization process. Maybe having a larger or deeper network just like kind of like interferes with the optimization process because there has to be too many back propagations over all the layers, right? If you have like 56 layers, you need to back propagate like 56 times versus 20 times. So there's like a lot of like gradient vanishing problem and gradient explosion problem. There's a lot of like bad behavior that could occur while backpropagating 56 times. So that's probably the cause of the problem, not overfitting. That was the core idea that the authors of ResNet focused on, which is an accurate diagnosis of this phenomenon, in my opinion. So what they did is let's just try to learn a residual transform. Let's see. Residual mapping. Okay, so residual mapping is the correct term. Residual transformation is a little bit weird. Yeah, residual mapping. So what before ResNet, what people did is you have an X input, you have an input image, and then you have conv and rel, and you have a bunch of like layers and on, right? But instead of doing that, let's have a skip connection between input and output. So let's assume that your single block consists of conv, rel, conv. So this is your input, this is your output, and this is your function. Then having a skip connection between your input and output of your function would make everything so easy because if you don't need to learn anything, if your model has learned enough transformation, it has done enough distorting or warping of your latent space, then all you can do is just using this route and do nothing here. You don't have to do anything here. You can just skip this part and then just go to the next go to the previous layer and do it so on and so forth because you already have this skip connection which gives you the same identity function, right? So this one kind of like acts as an identity function, and all this function has to do is just learn the difference between the identity function or the residual mapping. So this guy needs to learn only the small difference between the layers. Before before the skip connection existed, this guy had to learn both identity and the difference at the same time, right? Imagine this guy has to learn identity function, which is a very weirdly looking matrix, right? It's a zero matrix with only the ones in the diagonal, right? Learning this kind of weird matrix shape in using this convolution operation would be very, very hard. But if you ditch that, if you put that aside into the skip connection, the identity function being in the skip connection, then all this function needs to learn is the difference. So it's the job of this function has been way more simplified. So that is why the optimization is way more simplified, and then you can use like hundreds of layers, maybe 200 layers, maybe 300 layers, and so on and so forth. So that's the whole idea behind residual connection. So yeah, I think I've already explained the core idea of ResNet or residual connection. So there's like connection between here and here and here and here, different blocks basically. Right. So the further details, if you're interested, you can look at them. You can study the slides later, or you can actually read the paper. The ResNet paper is one of the best papers that I read. I mean, the writing, I mean, the idea is already like very nice and the performance is nice, but some papers, even though their material is like the content is nice, their writing or their presentation is a little bit lacking. But ResNet is such a well-written paper. Like just reading it is just, it's a pleasure to read the paper itself. So if you have time, maybe you can read the paper, even though it's a very old paper. It's still like it has a lot of nice ideas, and also it's very well written, like a story basically. So it's not much of a hassle to read. It doesn't like burden your mind. So I strongly recommend reading the paper if you have some time. Right, and we can, due to the lack, we're running out of time, so we're gonna have to skip. I want to show you this particular picture. Yeah, right here. So this is accuracy versus parameter size, basically. So this is like the larger the circle, the larger number of parameters the model is using. And you can see that AlexNet is using at least how many? Like at least like 65 million parameters. And it's only achieving 55% top one accuracy score in ImageNet challenge. So it's a very inefficient architecture. It uses a lot of compared to like, compared to like InceptionNet and ResNet, it uses way smaller. It uses like between 5 million to 35 million. So probably like 20 million or something. Compared to 65 million, this architecture, this is way more efficient than these AlexNet. So you can see that the CNN architecture, the design and the efficiency has drastically evolved, improved over like 3 or 4 years. So you can see that the whopping accuracy increase and also decrease in the model size. But unfortunately, now we're living in the transformer era. So again, we're using way more parameters than CNN architectures, but we're getting better performance than CNN architectures. So there's a trade-off as well. All right, so thanks for staying around. And yeah, I'm sorry I've missed a bunch of details, but just not enough time to go over all the nitty-bitty details of different architectures. So I strongly recommend that you study the architectures if you're interested, and please participate the practice session this Thursday so that you can really get a feel of actually implementing CNNs and training it, whatnot. Right. Are there any more questions before we end the class today? I'm going to wait 10 seconds or so in case someone is typing in. All right, I guess there are no questions. So so the next week is it's a project week, so there are no classes. So I'll see you guys the week after next week. Right. So good luck with the project, and yeah, try to attend the project spec session, the announcement session, so that you can ask questions if you have them. Right. Thank you guys. See you later. Bye bye. 감사합니다. 네.